What's the relationship between your hand span from your thumb to your little finger and your height? Well, we had everybody in the AP Stats class measure their hand span and their height, and we did it in inches. It says in centimeters on here, but I changed to inches because we already knew what our height was in inches. And we made a scatter plot. So how do we do that on the calculator? So if you go to your calculator and go to your list and spreadsheet page, you're going to title one of the lists hand span and the other one height, and type in your values. And make a scatter plot. So we're going to go to menu, or sorry, escape here. We're going to go to insert a page, control doc, and we're going to insert a data and statistics page. We click on hand span because we're going to use hand span to predict height. So hand span would be the explanatory variable and height would be the response variable. Okay. Now I noticed kind of a slight curve in this data. It's a little bit, it's not the greatest data in the world because we only had 8 of us, but we're going to use this as an example. We're going to do a linear regression. So on your calculator, one way to do a linear regression is to go from the list and spreadsheet, or sorry, the data and statistics page, go to menu, analyze, and go to regression. And then notice there's 2 types of linear regression. The algebra one that we typically do is mx plus b, but statistics we do it a plus bx, and that's because of the way the formula is designed on the AP statistics page. So we're going to use that one. So here's our equation. Another way to get the same equation is to go to a calculator page and do a regression on the calculator page. So if we go menu, statistics, stat calculations, and then go to number 4, linear regression a plus bx. Choose your x list, hand span, your y list, height. Also notice that the regression is being saved in this case to F2. Yours might say F1 if it's the first regression you've done, but I'm going to notice that and use that later. And notice it gives you the form of the equation. It gives you the a value, which is the y-intercept, the b value, which is the slope, the r squared, which we'll talk about later, and the r, which is the correlation. It also gives you a residuals list, which we'll talk about later. So those are the 2 ways to do a regression on the calculator. So coming back, and I think I'm going to pause for a second and copy the other regression page onto here. So okay, now we're going to talk about how we write about a linear regression in AP Stats. So first of all, rather than identify x and y separately and then write the equation in x and y, although you can certainly do that, you can certainly say x equals hand span in inches and y equals height in inches. We can say height equals the y-intercept plus the slope times hand span. Just actually put the words in the equation. So this is more the typical way you'll see it in statistics. This symbol over height means it is the predicted height rather than the actual height. So we're using the actual hand span then to predict the height. So the predicted heights would be on the line, the actual heights would be in the data values. So this, we call this y hat, or in this case height hat. Now we want to interpret the slope and the y-intercept. So recall that y-intercept is the change in y over the change in x. So this, in this case, it would be the change in height over the change in hand span, but usually that gets reduced then to change in height per unit of hand span. So we write the linear model predicts an increase of about 2.95 inches in height for every additional inch of hand span. It's very important, these words I underlined. A linear model predicts the height. This is not the actual height, so we need to say predicts. It predicts an increase of about 2.95 for every additional inch of hand span. In other words, it's not just 2.95 times the hand span equals the height, because in that case I have a hand span of about 8 inches. This is about 3. That would make my height 24 inches, which would be ridiculous. There's a y-intercept involved. So it's saying as hand span increases by 1, height increases by about 2.95. So we have to say it that way. We also have to say predicts because, and this about, you know, we have to say this is an estimation, this is not exact. So we have to use these words to indicate that this is an estimation, a prediction. For the Y-intercept, the model predicts a 45.64 inch height for a 0 handspan. Well, this is clearly ridiculous. So if the Y-intercept only makes sense if the X value or the explanatory value can be 0. Many times it cannot. So in that case, that would not make any reasonable sense. Okay, now we can use the regression equation to predict the height of a person. So I'm going to say, let's say this person who left the suspicious handprint in my room. I had a handprint and everybody measured it. It would turn out to be 6.25 inches. So just to show you a couple ways to predict, a fast way to predict on the calculator. Once you have done a regression on the calculator page, if I were to go up here and go to the right, you'll see that this equation has been stored in F2. So if I would type in F2 of X, you'll see that I get the regression equation that's shown up here. So I can type in F2 of 6.25. Now you can also just type in the whole equation and put the value. I can just put the value in for X, but this gives me 64.09. So this is saying that the model predicts that someone with a 6.25 inch handspan has a height of about 64 inches. So we decided, for those of you listening on another year to this, that the person in our class who had the small height here, it's probably her. Except her handspan was actually larger than that. But she was the one. It predicts that someone who's about 64 inches tall left the suspicious handprint in my room. We're going to assume that this was the crime scene and somebody left a handprint because they'd stolen something. Okay, in our previous notes we looked at some long distance jumps as compared to sprint time. So a person's sprint time in seconds for the 40 yards compared to their long jump in also in inches. And so let's I did a regression for this. So let's interpret the slope in the Y-intercept again. So this says the linear model predicts a decrease in this case, so that's a negative slope, a decrease of about 45.74 inches in the long jump for every 1 inch second increase in 40-yard sprint time. So in other words, people who take longer to sprint, so they're slower, probably don't have as long of a long jump. The Y-intercept, the model predicts a 414.78 inch long jump for 0 seconds in sprint time. Once again, ridiculous, or ridiculous as they say in Harry Potter. The Y-hat then, if we looked at, then the next question was, use the regression equation to predict the long jumps distance for a student who runs 40 yards in 5.78 seconds. So we see here that point is right here, and we're going to refer back to that in a little while. Y-hat equals, and we put the value in, and we get a predicted long jump time, or long jump distance of 150.39 inches, which is clearly less than the actual time here. And so we'll talk about that more later in the notes. Okay, going on to the next page. One thing we have to be careful of is, let me kind of get this off of here since we're not ready to talk about that yet. Is what happens when we do something called extrapolating. So for example, let's say I wanted to predict the long jump distance for a person who ran the 40 yards in 9.5 seconds. So when I do that prediction, I get a negative number, which is clearly ridiculous. It's saying somebody who runs pretty slowly jumps backwards. They can't jump forwards any distance at all. That makes no sense. It turns out when you extrapolate or predict a value that is outside of the range of the original explanatory variables that are in your data, sometimes those predictions are not very accurate. So you have to be careful about that. And I have a little cartoon that shows something kind of ridiculous, okay? My hobby, extrapolating. Yesterday you had 0 husbands. Today you have 1 husband. If we were to make a linear regression through those 2 points, you'll see that by late next month you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. Clearly ridiculous. Okay, so now let's talk about what we were talking about on the previous page. When we calculated the long jump distance for the person who had a 5.78 second sprint time, we got only 150.39, but their actual long jump distance was 173 inches. So we have what's called a residual. The residual is the vertical distance between the predicted y, the y, that would not be the predicted y, that would be the actual y, between the actual y and the predicted y for a given value of x. So when we subtract, we end up with a residual of 22.61 inches. So the interpretation of that residual is that this individual jumped 22.61 inches more than the linear model predicted. Or we could say that the linear model underestimated his jump distance by 22.61 inches. My caution for you is when you are dealing with interpreting a residual to look at the graph. It is clear from the graph that the person jumped higher than the line predicted. But sometimes when you're only looking at the number, you forget whether the point was above or below the line, and sometimes people accidentally subtract the wrong direction and then they misinterpret the residual. So make sure to always look at the graph so that you don't make that careless mistake. So what if we calculated our own residuals? So if I calculated the residual for my height, my handspan was 7.75 inches. So my predicted height is 68.5 inches. My residual is actually very small because my actual height is 69 inches. So I'm only slightly taller than predicted by the model, but it's a pretty good prediction for my height. If everybody predicted their residuals, what we would find out is that the total amount of distance above and below the line is always going to balance. We don't always have the same number of points above and below the line. In this case we do, but we don't always. But what we should notice is we have the same amount of residual on both sides of the line. The residuals, in fact, always add up to 0. If you go back to the calculator, one of the things you get when you do a regression on the calculator page is a residual list. So if I go to the variable button, the most recent regression I have is stored in here, and if I go to stat residual and push enter, it gives me a list of all of the residuals for this particular regression. If I take a sum of those residuals, so I'm going to go up and capture that and do a sum, I should get 0. Well, this isn't 0, but it's 0.0. If I were to type in there, this is 0.00000000019 with a negative in front of it. It's just a negative number. But that is for all intents and purposes 0. This is a case where your calculator had some rounding error dealing with with all of these numbers that didn't come out exactly 0, but it's supposed to be 0. So because those always add up to 0, then to figure out what the line of best fit is, I obviously want to minimize the residuals as much as possible, but I can't minimize the residuals by merely adding them up and saying what's the smallest number, because they're going to add up to 0 with the line of best fit. So what I do is I square all the residuals, very much like we did with standard deviation when we talked about how much different values of variables varied from the mean. Well, some of them varied above the mean and some of them varied below, and when you add them up, those variations always added up to be 0 because that was the definition of the average. So the very same thing, by definition here, these residuals are going to turn out to add up to 0. So we square them all. The line of best fit is called the least squares regression line because it is the line that minimizes the sum of the squared residuals. You can see this number on your calculator by going to your page where you have done, I'll find the one that I just did, the regression. Once you've done a regression, then you can go to Menu and Analyze, and then the residuals will no longer be grayed out. You can say Show Residual Squares. And so that shows the squared residuals and the sum of the squared residuals. We'll pick up with more of section 3.2 in our next video.